Okay, welcome to Related Rates, part 3. So sometimes in these physical situations, you end up with more than two quantities being related and changing, which means it brings in a product rule and you need to know a bunch of information in order to find one rate of change. But if you can come up with more than one equation, you might be able to create an equation that only has two quantities, and then you can find a related rate. And some of these problems are like that. This first one, this is just a circle, and we've done these before. But what you want to do with these guys is write down the stuff you know versus the stuff you want to find, and then once you do that, you can go ahead and write the equation you need in order to find a rate equation. Now in this case, you're told about the change in radius and you want to find the change in area. Now when you're asked to find a rate, there's going to be a moment in time that you're looking at, and it's usually based upon the measurement of some quantity. Like in this case, you want to know how fast the area is changing the moment when the radius of this circle is 5. This piece of information you don't want to use until after you have the rate equation. Like don't plug in 5 right away and then try to take the derivative, because now you just have numbers and there's no rate in your derivative equation. So take the derivative of this, and then you'll need to know what R is in order to find dAdt. Now, number 2 is a circle, and it's going to work the same way. Okay, now number 3, these questions get good. I like these questions. All right. In this one, you have water being poured into a conical paper cup. Now, if you're going to make a paper cup that's a cone, the cone's going to have to be upside down. All right, so this big cone represents the cup. Now, the dimensions of the cup never change. What's growing is the cone of water that's inside the cup. So when you're writing these equations with variables, you're representing the relationship between the quantities within the cone of water, not the cup, but the shape of the cup determines the shape of the cone of water. So you can use that when you're writing your equations. All right, so the cup is the height is 10 and the radius is 10. So my picture's not quite to proportion, but so it's, twice as wide as it is tall. Same thing with the water. I mean, it has a form fit in here. So the cone of water and the cone of cup are similar. They're in proportion. So the thing you know is that the cup is being filled, so the water level is rising. So the height of the cone of water is increasing at a rate of 2 centimeters per second every second. This is constant, which means the water must be coming in faster because you take more space the higher up you go. But okay, at what rate is water being poured into the cup? So if you're pouring water in, you're increasing the volume of water in there. So you're being asked to find dV dt, and you want to find that at the moment that the water level, the height of the water cone, is 8 centimeters. So this is like your instant information. It's not constant. This is only at a moment of time. So you say, okay, I want to know dH dt. I know dH dt, and I want to find dV dt. So I need an equation that's going to relate V and H. Okay. Well, the volume of a cone is 1/3 pi r squared h. And I said, okay, now I want to take the derivative of this, but this equation has both r and h in it. The radius and the height of that water cone are both changing over time. They're functions of the variable t. But I don't know anything about r or dr dt down here. Right? So that's going to be a problem when I take the rate. But in this particular case, we have this similarity relationship. The cone of water and the cone that the water is in, the cup, are similar. Right? They're in proportion. So I know this. If I take a ratio of radius to height of the water cone, it's always going to be in the same proportion as the container. Right? 10 radius, height 10. So they're 1 to 1, 10 to 10. And if you cross multiply, and then you'll get 10r equals 10h, which means r equals h. This is your secondary equation. It relates these two variables. And that's good because now you can replace one with the other. You say, well, I know about h. I know the rate of h. So it'd be nice if this equation just had h's in it. Didn't have the r. So I'm going to replace r. So v equals, now 1/3 pi is the same thing as pi over 3. And that's just a number, so it's easier to work with that way. And now I'm going to replace r with what is equal to in terms of h. Right, so now I can simplify that. Pi over 3, and then h squared times h is h to the third. Okay. I now have an equation of one variable. So now when I take the derivative with respect to time, I'll get dv dt, and I'll use the chain rule over here, and I'll end up with a dh dt. I'll also have some h's in it, but that's okay because I want to find it when h is 8. I'm looking for this, and I know dh dt. So when you have an equation of more than one variable, if you can find a secondary equation, you can make your life a lot easier. Take it from there. Okay, this guy's just a sphere, and it's just increasing the radius. There's only one quantity for a sphere, and that's the radius. So you know dr dt, and you're trying to find dv dt. Straightforward. Okay, sometimes now you can just get crazy. Sometimes a description, you just have to kind of turn it into a math model that makes it so you can work with it. So here's a guy, 7 foot tall. He's walking away from a light pole. Now if you walk away from a light post that's shining at night, whatever, the light comes out of the light post, and all this light down here gets blocked, and it makes your shadow. Right? So the shadow is over here. That's the length of the shadow. Okay. He's walking away. He's walking this way. So this distance between him in the light post is changing, and that will be his speed. Okay? That's the rate of change in his distance from the light post. So if I call this x, then his rate of change, the rate of change of x is dx dt. Both the length of the shadow and the length of the distance between the man and the post are functions of time. And now if you just take this picture with light post and person, you just turn it into a right triangle. There's the post, there's the man. Okay? Post is 20, man is 7. That's an S, and that's X. You now have a right triangle that you can work with. And this is all, the man standing straight up. Okay, so you have this big triangle, and you have this little triangle in the corner. They both share that angle right there. Big triangle, little triangle. They both have right angles in them. So they have two congruent corresponding angles, which makes them similar, which means the sides of the triangle are in proportion. So again, just like the one with the cone, we're going to be able to use that proportion to write a secondary equation. All right, so at what rate is the length of the person's shadow changing? So we want to know this. All right, length of the shadow. So we're trying to find ds dt, the rate of change in shadow length. When the person is 16 feet from the lamppost. So when x equals 16 feet. Now everything needs to be measured the same, feet, feet, second, second. So our solutions, the units is going to be feet per second. And I know, let's see, is 5 feet per second. So the person is walking away, so I know dx dt, and it's growing, so it's 5 feet per second. My camera stand's getting a little shaky. I'm going to fix that after this. Sorry about the earthquake happening at the same time, but it's a rate of change. So let's see. I know dx dt, and I want to find ds dt. So I need a relationship with x and s in it. So I'm going to use right triangles, and this is x and that is s. So in this big triangle, height over base must equal height over base in the smaller triangle, and that's s. Okay, that's cool because that's an equation with just two variables in it, x and s. And I know one of those rates, and I want to find the other. These are to the first power, so they're not going to be necessary maybe in the final rate equation, but I do know 16. So if I know 16 is this, if I needed to, I could figure out s. But I'm not going to plug them in until after you take the rate. So these are s's, not 5's, but if you cross multiply, 20s equals 7x plus s. Now, if you distribute and then combine like terms, you can get blank s equals something with x in it, and then you can take the rate. Find the rate equation, and then find the rate you need. problem set would be complete unless you were to talk about rockets being launched. Alright, so we got an observer. He's 700 feet away from the launch pad. The rocket blasts off and maintains a velocity of 900 feet. So the rocket's on the ground and it's taking off perpendicular to the ground. So if I call this distance y, the change in the distance y, dy dt, is the velocity of the rocket, upward velocity. Right triangle, how fast is the observer to rocket distance? Observer to rocket distance is right there, changing when the rocket is 200 feet from the ground. So you want to find, if I call this d, you want to find d dt at 2400. Right, so you say, okay, I know dy, I want to find dd. There's my d and my y. This is a right triangle, so y squared plus a number squared, doesn't matter, 700 squared equals d squared. And now I want to just go ahead and find the derivative. Okay. Y is this distance changing over time. D is this distance changing over time. 700 is not changing. That's a constant. Derivative of a constant is 0. This angle is also changing. If you think about the observer keeping his eye on the rocket. So another question that's not on there would be to find d theta dt at the same time. A little extra thing for you to think about. Okay, so over here, let's see, theta, you know dy, and you want to figure out theta, and you don't want to introduce any other variables if you don't have to. So this is the opposite, and that's the adjacent. Wow, look at tangent. What are the chances that in calculus you would use tangent? Opposite over adjacent. Y over 700. Now if I multiply through by 700 just to make the equation easier to work with, there's an equation that you can use to find the related rate equation. Okay, so there's some hints. 6 problems. Work on them over the weekend, and let's make them due on Monday. Thinking we should probably have like a Zoom meet. I'll send a post. Enjoy. Talk to you soon.